Hey all. So let's go to some of some of the problems, chapter 21. I don't think I have time to go over all of that in the classroom, so you guys can work with me outside the classroom on it. So I just browsed through the book and I got some problems, and here where we are. So so this is the positively charged rod, and then you have two uncharged spheres, right? And they are in contact. So when you bring this, so what's going to happen? Oh, so you bring the rod, and then you separate those two, and then you have questions. What's the final charge in X and Y? Well, so since it's metal, so we are talking about conducting material, right? So if it's a conducting material, electrons can rush around. This is positive, so we're going to have a bunch of electrons coming over here. We're going to have a lack of electrons in this part of the sphere, right? So when you separate them after you eliminate, um, while you keep the rod nearby, so you separate them. So this guy has, this guy will have a excess of electrons, and this guy will be lacking electrons. Okay. Now I could ask the same question. What if you have insulators? What if you had insulators? What would happen? Um, well, if you don't have a good answer here for insulators, you can go to the lab and play. So what is this? You have a positive charge Q fixed on a very large horizontal frictionless tabletop. Second positive point charge, so this is positive. A second positive point charge is released from rest near the extension area. So this is Q, this is not fixed, so it's released. They are both positive, so charge Q experience a Coulomb force, um, and it's just gonna go, right? It's just gonna go. So that's the Coulomb force. Every time you have a force, you have a acceleration on it. So assume that gravity is not doing any trick here. Gravity force is negligible. You can consider that electric force is the only one. So what do we know about this? I think it's asking about motion. So once giving a certain distance, the force, the moment you place the charge there is equal to a constant product of the charge, distance is square. And if the electric force is the only relevant force, this is equivalent to mass of electron times acceleration. So you can see that your acceleration will be dependent on r. So in fact 1 over r squared. So essentially if you plot if you plot a graphic acceleration with position, right? So you would have some decaying acceleration done that way, okay? With the maximum value at this point. So which means you have a motion in which acceleration diminishes all the time. If you call this direction a positive one, your acceleration is positive, right? And and so it's velocity because it's going in the positive direction. And if you recall your physics 4A course, when velocity and acceleration both have the same sign, you have a speeding up process. So once you release the particles, in fact, the particle q, lower q, it's going to be speeding up all the way, right? From some initial velocity naught up to, I don't know, God knows what. So then you choose one of the options here. A piece of plastic uh, has a net charge. A piece of plastic has a net charge Q. Right, oops, microcoulombs. Okay, how many more protons than electrons does this piece of plastic have? So the charge is positive, so it has more protons, right? So which means this sphere has lost certain amount of electrons to become negatively charged, and each electronic charge is that one. Okay, so which means the number of electrons that left the sphere times the charge of one of the electrons is equal to the total charge in that sphere. Right, and then you can find the number of electrons. So what is this? We have a 3-point charge. Oh, that looks like the problem we did in class. So we have 3-point charge. So you take the origin, and then you have a positive charge at the origin. You have a negative charge that is placed 50 centimeters away, and this charge is a negative one. And you have a positive charge that is placed here. That is a positive charge. We write up here for 10 to minus 6 coulomb positive at 1 meter mark, right? 1 meter mark. What are the magnitude and direction of the electrostatic force that acts on the charge at the origin? So you want to find out what's going on here. So some students, sometimes they get all confused because they forget the concept learning physics 4A. When you do a free body diagram on a charge, forces are superimposed. So you don't need to find out what's going on here or going on there to figure out what's going on here. So when you do a free body diagram on the charge that happened to be at the origin, you just ask, okay, which action this particular charge is doing on this charge? And then you ask the same question again for the second one. So basically, let's do a free body diagram on the charge that happened to be at the origin. Let's call this charge 1. Let's call this charge 2. So charge 1 is a negative charge. Charge 2 is a positive charge. Therefore, they have an attractive force. I'm going to call the force 1, F1. The magnitude, which means the number of this force, that quantify this force, is given by K times product of both charge. See, it's magnitude. I'm not caring about sign, right? I'm not caring about sign. Product of the charge divided by the distance square. Don't forget the square. So I have the magnitude of the force, and I know because of the charge they have, they happen to be attractive. So charge 1 is pulling the charge at the origin to the right with a force F1. Now, I go to work on the free body diagram of charge number 2. Charge number 2 is a positive charge. Charge number at the origin is a positive charge. They repel one another. And so, which means, let me call the magnitude of force of charge 2 on the charge at the origin, F2. That is going to be K times 2, 10 to minus 6 times 4, 10 to minus 6 divided by distance squared. Very important. I'm not worried about signs. See, signs on the charge because I already indicate the directions of forces in the diagram. So I really, as of now, I'm not thinking about how strong those forces really are. I'm just worried about the direction. So that's why I'm representing this vector kind of a big or not. So I really don't care. So if I call to the right positive orientation, then the resultant force, and that's what we want to find, is given by F1 minus F2, F1 minus F2, and the positive x direction. And then what you do next is to take this number, plug it here, take this number, plug it in there, and then problem solve. If if you find a negative number, it means F2 is stronger than F1. And then the particle at the origin is supposed to go to the left. Otherwise, it's going to go to the right. In the figure, all the charges are point charges, and the charge in the middle is negative. So Q. Yeah, sorry. I had to step out for a second. So I think we did number 5, right? So number 10. In the figure, all the charges are point charges, and the charge in the middle is Q. So the negative charge, oops, it's a negative charge. Negative charge. And for what charge Q1, for what charge Q1, so Q1 is our unknown. So we want to solve for Q1. Will Q2 be in static equilibrium, which means whatever forces that are acting on Q2, these forces must balance out. So we take Q2, and Q1 is negative. So let's call F1. Let's call F1 the force of charge Q1, and that is equal, I don't know direction. I'm assuming let's say, let's make an assumption. Q2 is a positive charge, okay? If Q2 is a positive charge, then Q1 must be also positive, so that F1 goes to the right, and Q2 as a positive charge will be attracted to the big charge Q. Call this FQ. So F1 is K, Q1, which we want to solve for, Q2 divided by distance squared, 20 centimeters. and FQ is equal KQ, absolute value, Q2 divided by 0.1 square. So we want these two magnitudes to be the same, right? Opposite directions, so they cancel out. That's guarantee that Q2 is in equilibrium, which means we want to F1 equal FQ, or K Q1 Q2 divided by 0.2 square to be equal to K Q Q2 0.1 square so Q2 goes away, K goes away, and then we can figure K1. Okay, I'm back. So we have a figure two 5-gram spheres. The thread has 1 meter long thread, so we are talking about tension when you think about forces. And we have two equal charges, so we are talking about repulsive forces. And we have to solve for the angle. So solve for an angle. So let's do free body diagram. The force is acting on one of these spheres, F, tension. There is a gravity force as well. And since they are of equal charge, there is a repulsive force, FQ. Coulomb force. So we can write expression for FQ. FQ is 9 10 to the 9 times the product of the two charges divided by distance squared. We can call this D. And then that's going to be 2D squared. This is K Q squared divided by 4D squared. So notice in this expression only D is a null, so we don't know D. In fact, to solve for an angle, we know that tangent of theta, sine of theta, it can be written as a function of the geometry of this triangle, right? So sine of theta is d over 1, cosine of theta, it is what? Square root of 1 minus d squared divided by 1. 1 is the hypotenuse, and we have tangent of theta. Tangent of theta is equal d over square root of 1 minus d squared. Okay. Fg, the weight of this pitball is mg. This is a known quantity, right? So we know that one. 5 10 to minus 3 times 9.8, all of that in newtons. Okay, so let's remember how to solve this problem as far as our physics 4a is concerned. Call your axis and its regular direction as positive, and then start, working sum of forces in x. Assume it's in equilibrium is equal 0. So FQ, which is here, is equal to T sine of theta. If you are not comfortable with this projection, please talk to me or please go to tutoring. If you studied this a long time ago, and might be your case, then you really should spend some time trying to remember and practicing this math. Otherwise, it's gonna be in your way of your physics, and you don't want that. You want a math to help you, not to put you down. So FQ is equal T sine theta. So what you want is this force is equalized by the projection of tension along the x-axis. So this tension projects as a force in that direction, right? In fact, my diagram, as you can see, is not well drawn because the size of this vector should equal the size of this vector, but sorry about that. But that's what we got. So, and then what? Now, if we do sum of forces in y equals 0, then the projection of tension along the y direction, which is t cosine theta, is equal to mg. So this projection here of tension balance out the weight, basically. Now we have to solve a system of two equations and two unknowns. We don't know the sign. In fact, three unknowns. We don't know the sign, we don't know t, we don't know d, but we can write sine and cosine as a function of d. So basically we have two equations and two unknowns, so technically we should be able to solve. We could eliminate one of the unknowns if we divide this equation by this equation. If you do that, t divided by t cancels out. We have sine theta over cosine theta equal sine theta, t sine theta is fq, which is k q squared divided by 4 d squared divided by t cosine theta, which is mg, right? Which is mg. So divided by mg. So fq divided by mg. And sine of theta over cosine of theta is tangent of theta, which is d over square root of 1 minus square root of 1 minus d squared. So pretty much that's it. Okay. All right. Oh God, how to solve that? So now we have just, if you look at here, we have one equation and one unknown, right? Because we converted theta as a function of d. How can we do that? Well, we could square all of this nonsense. I mean, for k q squared divided by 4 mg, this is a constant, right? It is some constant. Let me call this constant c for constant. So if we can do that, then I have c over d squared is equal d over square root of 1 minus d squared. How about if we square every one? D c squared over d to the 4 is equal d to the second wait a second. Sorry, I'm back. I keep being interrupted. But anyway, so where we were, so we got to this equation, and now I have to solve. Um, and then you find d, and once you find d, you can find your sine and then your angle. This looks like something similar. You have a sphere. The mass is given, so there will be a force there. So let's do our free body diagram to begin with. Oh, wait a second. Let me read the problem first. So we have a spherical insulator, the mass is given, the charge is given, and is hung by a thin wire. A charge, negative charge, is held a certain distance away. So the wire makes an angle theta. And again, we should find the angle. It's the same idea. It's exactly the same problem. So you take this guy, do a free body diagram, mg, and then you have tension. And then the forces here are attractive. Basically the same problem. Okay, same problem. Small sphere, mass is given, is moving upward along a vertical y-axis. When it encounters an electric field, so we have the magnitude of field, but we don't have direction. So if due to this field, the sphere suddenly acquires a horizontal acceleration, so horizontal acceleration, the only thing we know with this is that the net force along x direction is also pointing that direction. Why? Because this net force is equal to m. Is that an electron? Oh no, it's a mass, it's a sphere. Because this sphere has a mass, right? Times acceleration. So let's, and we have to find the charge. So we want to solve for charge. So let's outline this problem. Vertical direction. We have a little mass that is moving up, right? It's moving up, and suddenly feels a field, and the only thing we know is that net acceleration is here. Which means the net force is in there. Now, if gravity pulls this sphere downward in a vertical direction, right? So the electric field has to be what? So we wanna sum two forces. So we have a vector A downward, and we have a resultant vector to the right. So which means if we have a vector like this, and we have a electric field like that, right? Wait a second. If I'm thinking aloud, if you have a vector like that, if we have a b vector in that direction, then the resultant vector, which is given by adding the tail of the first vector to the head of the second vector, right? This is the resultant, and it could be horizontal. In other words, then the electric field has to be something like this. right? So, but what is the electric field? How does it relate to force? That fruit, remember the fruit kiwi? The electric force, and that is what goes in a free body diagram, is the electric force. That is equal to QE, QE. So if we define the direction of our electric field, then we know the direction of electric force, and that's a QE. Okay. We don't know the direction, so we call an angle theta. That's the beauty of algebra, right? So based on that, sum of forces in x, don't tell me zero, because it's not. It's not in equilibrium. Sum of forces in x is equal mass times acceleration in x. So what is the force in x? Q E cosine theta. Q E cosine theta. And what do we know? We have acceleration and we have the mass, right? We have the mass, and I'm converting here to kilograms. And the acceleration, I do have 13 meters per square second. So in this equation, we want to find this. This is our unknown. We have electric field, but we don't have the angle. If we had the angle, problem would be resolved, but we don't. So where we go now? Sum of forces in y. Yes, very good. We have to project in the vertical direction. Sum of forces in y, there is no acceleration along that direction, which means it's zero, right? Sum of Newton's second law tells us that sum of forces is equal ma. Acceleration in y does not exist because the net force has an acceleration in x. Therefore, we can proceed making the proper projection. So QE, the fruit, sine of theta is equal mg. Okay. So look at this. We have the mass and we know g. I mean, we still live in planet Earth. Gravity is 9.8. So if you divide these two equations, QE, the fruit goes away, and of course you're going to be hungry without your snack, but you have a tangent of theta that is a number, right? mg you know, and this is a number, so you know tangent theta. So if you know tangent theta, you know theta, and then you can plug it back here, and then you can find the charge. In the figure, you have a ring, radius carries a charge, Q is given uniformly distributed over a point Q. Oh, we did this in class. A point Q is placed at the center of the ring. Oh, we have a charge there. We didn't do this in class. The electric field is equal to 0 at a point P. And the distance here is given 0.73 meters. And then we want to find Q. Oh, that's interesting. So first of all, it says the electric field at point P is equal to 0. What does it mean? Well, it means you could solve this problem thinking about electric field being 0, or you could even put a test charge at point P and then say, well, the electric force at that point is 0. Okay. So how do we solve this problem? So if the electric field is 0, what are the two charges, or what are the two charges distribution that are causing or producing electric field at point P? One is the ring. And we saw in class not for the electric field, but for the electric force. So uh, the electric field of a ring is equal to the electric force. A ring would produce at that point P on a charge Q, right? On a charge Q. So what you do, remember the equation we developed in the class. I'm not going to do it here. And I don't have my book here to copy the equation over. But if you go to the book, or if you develop the steps we did in class, you take the electric force divided by Q, the charge that was in class located at point P, and then you have the electric field. So the electric field of the ring is like that. Okay? And the expression you should know. If you don't know, you can develop. And the charge Q, right? The charge Q, so since we wanted the field here to be a zero, the charge Q must be a negative charge, because a negative charge creates an electric field that points towards it, right? And then the problem is basically solved. So what is the expression for an electric field of charge Q? Is equal to K Q over distance squared. And that should be equal to whatever expression you got for the electric field of a ring. And then you can solve for Q. I'm getting tired. A pair of charged conducting plates produce a uniform electric field given directly to the right between the plates. The separation of the plates is given. An electron is projected from plate A towards plate B with an initial velocity given, I show in the figure. Oh, there you go. We have a figure. Don't need to draw. Okay. Constants are given. The velocity of electron as it strikes plate B is closest to. Okay. Now, you have your electron right there with an initial velocity Δ1, and the electron is supposed to go all the way and strike plate B. Now, let's remember our concept of electric field. I mean, we haven't studied voltage yet and energy associated with this, which would be simple to solve. So we are going to use pretty much what you're studying in chapter 21. So the electric field, is to the right, like this, right? And the relation between electric field and electric force on the particle Q is the fruit, QE. So if you put an electron inside the plate, if you shoot an electron right here inside the plate, at the moment the electron gets inside this field, supposedly uniform right there, the electron will experience a force QE. But electron has a charge negative, so the force, I like to write force in red. The force will be like that. Right? The force will be like that. That is electronic force. And then you have pretty much the motion of electron to the right, velocity positive to the right. But the acceleration, if you draw the vector acceleration, is one that is changing all the, it is the one that's to the left, because the force, electronic force, is to the left. So because of this, fact that both vectors are in opposite direction, it means you have a decelerating situation. So we have a slowing down process, slowing down. Don't know. Yeah, the acceleration is negative, so you have a slowing down process. That's the first thing you have to know. The second thing is the field between those two plates is uniform, which means the force between them is constant, which means the acceleration is constant, right? So constant, constant, the acceleration is also constant. And it seems that the problem is chapter 2 on your physics for a book. So you can use Bernoulli, you can use all kind of things. So if you apply Bernoulli, v squared is equal v naught squared plus 2a x, right? So final velocity you want to find, initial velocity is given, what? 2.0 10 to the 7, and then you square that thing, plus 2 times acceleration. But what is the acceleration according to our Isaac Newton? Is equal to the force divided by the mass. Electron. And del x is, and the acceleration is negative, and del x is the separation between the plates, 40 millimeters. And then you can solve for the velocity. What else? So yeah, that's it. So I think that's the other one might be similar. Okay, very good.